I have more questions about that later, but
Okay.
yeah.
We'll talk about that later.
Oh, younger.
Okay. With these particles, the smaller particles, especially the interstitials, but it can be the substitutionals as well. When we have these other particles, one of the things that we find is that not only does it matter how much of those particles there are, but it matters what shape they're in. And so they gather together, and sometimes they'll gather together in long platelets, and sometimes they'll gather together in big spheres, and sometimes little spheres, and spread around. And that makes a huge difference to how the material, what its properties are. So if we increase the amount of the secondary particles that are in the material, you can see that the ductility goes down. So more secondary particles reduces the ductility. And it reduces the ductility because dislocations cannot move through the materials as well. They will hit the secondary particles and they will stop. But, yes?
Sorry, I just want to make sure I heard right. More of them decreases ductility.
Yes, I'm sorry. It decreases ductility, which means that we can't reshape the part as much, right? And so we try to reshape the part, and instead of reshaping, it will fracture. Now that may mean it's stronger. It doesn't mean that it's weaker. It may be that it resists, and it resists the shape change much better, and so it doesn't get to the point of beginning to yield. But when it does yield, it will more often be in a brittle manner or more like a brittle manner. And so we can't reshape it as much. And it matters not only how much of the particles there are, but what shape they're in. So these are different shapes. Names have specific meanings. We don't have to spend a lot of time on that, but spheres are spheres, and elongated or plates means that it is elongated or plate-like. So it is long and thin. What did we learn about crack propagation the other day? We talked about crack propagation. We talked about windshields with it.
Was it like the end of the crack is like smaller and smaller, so it's like infinitely increasing force on it, so then.
Okay, so yes, that's
Part of it.
on the way through. You're gonna answer sort of the same thing.
Kind of the same in the whole talking about the radius.
Okay.
And how a bigger radius means more area for the force to be spread across.
Okay, so the stress is lower because it's got more radius. So we talked about crack propagation on the surface of the material. That is, if it has a larger radius or is shorter, it's more resistant to a crack forming. In here, we can see that if we have plates, and you can think of the end of the plate as being kind of like a crack, because there's this problem in the material. It has these sulfides, this secondary material that is sort of forming a crack in the material. And so if it's in a plate-like shape, so it's very small and flat, it's going to have a sharp end on it. And you can see that the result of those sharp ends is that the material has a low ductility. It's not going to reshape very much before it just fails in a brittle sort of mode. If they're spherical, then it doesn't like to propagate those cracks, and so part of it is that it is more ductile. So you can see that spheroidal and pearlite, you can think of those as pearls, are up here, and they have more ductility. Yes?
Is this sort of inclusions, is this in steel? Is this in a generic metal? What's our?
So this is, the phenomenon happens in a generic metal.
Gotcha, yeah.
This is particular to steel for the specific things that it says with the carbides in it, but it is a generic to metals with certain alloying particles in it. However, steel is the one that we alloy in this way the most. Yes?
Wait, so I don't fully get it. Are you saying the spherical carboids are more more likely to be ductile than, for example, the elongated sulfides, or what?
Yes, so they have a higher ductility if it's spherical. And so higher ductility means that the part will change shape more before it fails. If you have these others that are plate-like or elongated, the ductility is not very high, even for a very low concentration. So, you know, a tiny percentage, and it has a very low ductility on the vertical sides of the graph. So when we look at the material, when we look at the steels, well, yeah, that's okay, we'll skip that. I mean, what this is saying, these are the different steel designations for the AISI sort of normal steel designations for the 1000 series steels. The last number that is in here is hundredths of a percent of carbon. That is a tiny percentage of carbon. So 8/100ths of a percent. So a percent is already 0.0, and so this is 0.0008 carbon. And with that, you can see that as you increase this, the percent elongation goes down and down and down. So the ductility is going down as you add more carbon in. The yield strength is going up considerably. So the material is getting a lot stronger as you put more of this carbon in. You'll notice also that this ends at a fairly low number. This is only for steel. It does not add enough carbon to get into the cast iron range, because that's a whole different kettle of fish. A cast iron kettle of fish. So as we look at this, I don't want you to memorize the different shapes and the different materials. What I want you to get from this graph is this material. You can have these inclusions in all kinds of different shapes. They will gather together in all these different shapes, or they may be forced into these shapes by the process with which you made them. So in between the grains, they can be surrounded. Each grain where nucleation started and it grew and it grew and it grew, it can be totally surrounded by the secondary particles. Or it can be where the grains, the boundaries are kind of indistinct, but the secondary particles are aligned within the grains, or they can just be spread throughout, very evenly dispersed, or dispersed in little spots, so it looks like a Dalmatian particle. And so what I want you to know from this is that all of these are options. There are options that they are things that happen with the material with an amount of secondary particles within the material. By thermodynamics, they can be distributed in all sorts of different ways, and each of these different materials will have different different strengths and different ductilities. So this could be the same material all the way across, and in this same material you can have a yield strength that's very high or pretty low. You can have ductilities, so the dashed lines are ductilities, so a very low ductility, medium, higher ductility. You can have all sorts of ductilities and all sorts of strengths with the same materials, just with the secondary particles distributed differently. So one thing we're going to work on is trying to understand how do we redistribute those particles when we need to.
As more particles are added, what happens to the strength again?
As more particles are added, the strength goes up, generally, until you get to a certain point, and then it all goes nuts.
What's homogeneous? I guess, what does that mean in this?
Homogeneous means that it is spread sort of as evenly as possible. I don't know why it has little lines going across it.
Okay.
It just looks cool. Makes us feel good. Yeah. Okay. So here is how we move those particles around. This graph has time on the x-axis, and you'll notice that it's logarithmic time. So it is getting from short amounts of time to huge amounts of time. And on the vertical axis is temperature. So what we're doing here is we're taking a material, we are never making it molten. So this is a solid material, and what we do is we heat the material up, and this is specific to steel that we're talking about here. You can do it with other things, but we'll talk about steel because it's such an important material. So we're going to take our steel and we're going to heat it up above the austenitic line. So this is called austenitization, which is a very difficult word to say. And it is because we're taking the material to the austenitic zone. As we heat this material up, the crystalline structure of the material totally changes. So it starts out maybe body-centered cubic and it changes to face-centered cubic, or it will completely change the structure of the material. We're not melting the material. So it is bizarre to me that the crystalline structure can completely change. Completely different size material, completely different structure to the material. And once we get it there, then it matters how we cool the material down. So if you've ever watched any of the shows where they make swords and things, they will always start by quenching the material, and then they'll heat it up slowly to temper it, and then cool it back down. What they are doing is they are quenching it, so they're taking it from this austenitic zone, and they cool it very, very quickly. That makes a material, it makes martensite, but it makes a material that is super hard and very, very strong, but has terrible ductility. You cannot do anything with it. It is just very, very brittle. So very strong, but very brittle. And in fact, it's not very usable there. So then what we do with it later is that we heat it up a little bit. We're not going back up to the austenitic zone, so this is tempering or can be normalizing, names for it. And when we take it up to this temperature and we hold it there for a while, we are diffusing the secondary particles throughout it. So when we cooled it off very quickly, we froze all those secondary particles, and they were stuck wherever they were from being in the austenitic form. They are stuck in those locations. And then we do this normalizing where we heat it up and we let them diffuse for a certain amount of time, and then we cool it back down. And by choosing the temperature and choosing the amount of time, that determines what shape they're going to diffuse into and how quickly they're going to diffuse. But that's not all we can do. We can take the material, and instead of cooling it really quickly, we can cool it slowly. If we cool it slowly, we get terrible material. And the reason that it's terrible is not because of the secondary particles, but it's terrible because the grains just grow to be huge. And so the strength of the material is really awful. It's very, very low strength material.
If you heat it,
if you cool it really slowly, the grains grow really huge and it has low strength, and it's just not good material for much of anything.
The grains of what, just material, why does it grow big?
Because you're holding it at a high temperature for a long time, and so the grains will consume the grains that are around them and continue to grow and form into bigger and bigger grains. Yeah. But we can do all sorts of weird things. You can do this one, this os forming, where you cool it really rapidly, and then you stop and you heat it and cool it and heat it and cool it and heat it and cool it, and then you hold it there for a long time. So what I want you to know from this graph is we end up with a set of a dispersion of these secondary particles, but we're not stuck there. That's the important thing to understand about metals. You are not stuck with what you get out of the process. We can take the material and we can heat it back up, we can redistribute the particles, and then by controlling the cooling and things like normalizing, where we heat it up for a little bit and then cool it back down, we can control what our material properties are. So we have a giant reset button, which is really useful, because when we start doing the different processes, we're going to do something to the material, and it's gonna cause the material to be really brittle. Really strong, but really brittle. And if we need to form the material more, then we need to press the reset button and get back to the original material properties that it had. And so heat is the way that we return the material to its original material properties. Heat and time. Questions about that? So things that I want you to know. I want you to know that we have a reset button, and with heat and time, we can get the material to change its properties. Is the material going to the liquid state? No, we are not remelting the material. So that's really important to understand. It's still solid material. We're heating it up, we're doing this process. What is the primary mechanism that is going on when we do this? Heat, but what's happening in the material? It's diffusion. So the particles are diffusing in all of this area down here. But remember, if we heat it enough, we also completely change the structure. And that structural change is going to cause the grains to change as well. And so if we take it up to the austenitic zone, we can reform the grains of the material as well as the diffusion. And so that gives us sort of two levels of reset button. One is to take it all the way up to the top. We reset the structure, we reset the size of the grains. We lose everything that we had before, but we gain all of our ductility back as long as we cool it correctly. Or we can heat it up just a little bit like this, and we can recover some of our properties, but not lose everything. So we're gonna use that a lot. Yes?
So we would not use austenitizing and annealing interchangeably?
Right, austenitizing and, well, annealing is part of the no, they would be separate. You can anneal something or temper something without going to the austenitic region.
Okay, thank you.
So what would be the definition of the austenitizing? Like, other than just heating it up above the austenitic zone, would it just be like heating it up to that certain point of the material with that property? Meanwhile, annealing is just cooling something down at a certain rate.
Annealing is heating to a lower temperature, utilizing diffusion to restructure the material. We're going to get to words that we talk about further in in 2 weeks. But what we will talk about is recrystallization. So when we take it to this austenitic zone, we reform the crystals, and this lower one is recovery, and that's where we just change the dispersion of the secondary particles. I don't want you to try to memorize any of these names or any of these pathways. There isn't a reason to do that. You leave that to a metallurgist, I leave that to a metallurgist. Anyway, we just need to know that we can change the properties of the material back by using heat. We should also understand that occasionally, when we don't want materials changed, they will change if we heat them. So if we have a process that introduces too much heat, it will change the material properties whether we want it to or not. And so we have to deal with that. This is just showing what I talked about a minute ago, that the grain size greatly affects the strength. So I wouldn't worry about the equation. You can just look at the graph. The graph says as the grain size increases, the strength generally decreases. So the upper graph here is if you're lower than half the melting temperature, the grain size decreases a lot. If you're above half the melting temperature, the strength decreases a lot. If you're at half the melting temperature and above, then you didn't have a lot of strength to start with, and the grain size or the strength decreases as you increase grain size here as well. There's a weird thing that happens on this lower graph, which we don't really have to deal with a lot, but yes.
Are we gonna have to like remember like for example what KY or like?
No, you're not. So what you need to know about this is that if the grain size increases, the strength decreases. Small grains, high strength, large grains, low strength. There is an exception. That exception is when you are at high temperature and a very low strain rate. So this is jet engines right here. So jet engines run at a very high temperature and a very low strain rate because it is spinning, and so there's this small amount of strain that is trying to stretch the jet engine blades. And so if you have multiple grains in those materials, they will fail eventually. And so jet engine or turbine blades are single crystal, so that you have the grain size is huge. It is the biggest you can get because there is only one grain.
What is the strain rate again?
The strain rate is how quickly you are changing the shape. So strain is the change of shape, and rate is how quickly. Okay. So, if we were to pour on the sheet of paper that you have before, I want you to think about if we were to take metal and to pour it into a mold and let it cool. So we're doing casting. The different topics that we talked about today, how would those topics affect the material if it was a non-eutectic aluminum alloy? So it's just stuff together, or it's aluminum and other things mixed in, which is almost all the aluminum we use. We never use pure aluminum. It's like chewing gum and it's not very strong. It's not very useful. What if it was steel? Maybe that has some difference to it. And what if a part that you were casting had really thick areas and really thin areas? What would be differences in those areas based on things we talked about today? So I want you to write some of those down on that sheet of paper that you drew Bellingham on.